So I'm doing recording.
I think computer is safer.
On the computer. I'm gonna go over a few basics because it's been so long since the last Aero workshop, um, because of the midterms and all. So quick review before we jump into the actual stuff. I'm going to share my screen. Let me know if you're not able to see it. Is everyone able to see my screen? All right, good. Now let me do a test. Okay, good. Um, so here today in the workshop, I want to cover a little bit more about airfoil aerodynamics, but um, a little bit more over 0 to 180 degree to like explain what really is the difference between a streamline and a bluff body. So it kind of like kills two birds with a single stone. Also, this discussion about 180 degree angle of attack aerodynamics will be useful when we do our aerodynamic analysis over a wind turbine because of the reasons that will become apparent in the future. Um, but for now, let's recall what a bluff body is as opposed to a streamlined body. So a bluff body, it's it's draggy. A best way to explain this is something that is big and bulky and not streamlined, right? So something like, for example, a cylinder is a bluff body. What is a streamlined body? It's a shape where you design the shape such that you encounter low drag. So something like an airfoil, which happens to be a streamlined body. Now, the difference between the two from a more technical perspective is the manner in which air flows over it. So for a bluff body, for example, if you have a cylinder and you have an incoming flow field, the flow tries to follow the surface of the cylinder up to a certain extent, but then after a certain point, it ends up separating and goes like this. So instead of following the surface of this cylinder all the way and going like this, it separates from the cylinder surface on somewhere near the top and then goes about its own way. And this kind of flow separation from the surface of the cylinder increases drag. And I'll explain why in a second, as opposed to an airfoil, for example, where you have um, the airflow following the contours of the shape, both above and below, all the way. Okay, now my claim is this bluff body will have higher air resistance as compared to something more streamlined, like this. The reason being, we can go to like Newton's second law, for example, where we have rate of change of momentum equals to net force. Everybody remembers this, I hope. It's from your high school. So if, let's say there's an object, let's consider a cylinder, and the air is flowing over it like that, obviously there is going to be an air resistance on this cylinder. So if I had to draw a free body diagram for the cylinder, it would be just this, right? Drag force, if we denote it by D. Now this D force is the force of air on the cylinder. So by Newton's third law, there has to be a force in the fluid there has to be a force on the fluid by the cylinder in the opposite direction like that. All right, so if D is the only net force acting um, on the fluid, then its momentum has to decrease in this direction, right? Because the net force is in this direction, so the change in momentum has to be also in this direction, which means the momentum here would be lower in the fluid. Please stop me at any point if you don't understand something. Is this clear? Why the momentum of the fluid before it encounters the cylinder would be higher than when it's downstream? Because the net force is in this direction, then the momentum change has to be in this direction. Um, so, and that is consistent, right? Because if you look at the flow field around the cylinder, here you have almost zero velocity. If you make a plot of velocity as a function of y, so this is x and this is y, and if you make a plot of magnitude of v as a function of y, so the in this region the velocity would look like this, where you have faster flowing air far away from the cylinder, but very close to in this region, because it's a dead air region. You're right behind the cylinder. The air would be moving very slowly in this region because it's separated. And that's why you have this dip in the velocity. So you have a massive loss in the momentum um, after separation from the cylinder, as a result of which you have higher net force, which results in higher drag. For a streamlined body, this region of dead air behind it is very small. This region of dead air behind an object is called a wake. It's called the wake region. So drag for a bluff body scales with the size of the wake. So let's say you have a square that is of a unit size, as opposed to a cylinder that is also a unit size. The flow separates for a square like this as opposed to like this for a cylinder. So the size of the wake, or the dead air region where the velocity is very slow, is smaller for a cylinder, and that results in lower drag as compared to a square. And if you have an airfoil now to compare, that is also a unit size, the size of the wake region behind it would be even smaller. That results in lower drag. So I am going to give you an exercise really quickly to really understand how much effect this streamlining process can have on drag reduction, for example. Let's say CD, you have a cylinder and you have an airfoil. The length of this is, let's say, 30 centimeter. The drag coefficient CD for this So let's say 0.005. CD for this is 1. Now I want you to find the size of this circle. Find diameter such that, let's call this object A and object B. Drag of object A equals to drag of object B. Okay, so I'd like you to find the diameter of the cylinder that will make the drag of this thing equal to the drag of the airfoil. And you guys can like, I'll give you like 5 minutes. It's not that hard. The equation for doing this is D equals to half times the density of air, which is 1.225 times V square. You can assume V equals to 10 meters per second times, so this is C, D, and this is C. So it's half, either C or D. So reference length half rho V square L times CD. So for drag, for A, it would be D, and for B equal half rho V square times C, CdV. So all you have to do is equate these two formulas. You know what C is, you know what CdB is, it's right here. You know what CD is, it's right here. You know what rho is, you know what V is. You can find out the D value. Um, so you're like, I'll give you like 5 minutes, and then we can like discuss.
We put it in the chat or shout it out or hold our tongue?
I'm sorry, what?
Should we put it in the chat or shout it out or just?
Either way, it's fine. Yeah.
Okay.
I hope you all remember what CD means. It's a drag coefficient, and the meaning of what these coefficients for lift and drag mean were explained before. So if you need to review them, you can look up previous workshops for revision, and then ask me questions if you have more later on.
Suraj, I don't know if you can see the chat, but Yusur was just asking you to say the last thing again. I think you were just saying if anyone has questions to ask you.
Right. I'm not monitoring the chat. Thanks
Yeah.
for bringing that up. Could you please, the last thing you said, if you don't mind? Oh, I said the drag coefficient here. This is not going to show. Right here, CD, the CD value, it is a drag coefficient. And if you don't remember what that means or don't know what that means, this was explained in previous workshops. But if you have a question now, I can quickly tell you that it's a measure of how draggy a shape is without considering its size or how fast it's flying. So something like this that has the same size as something like this would be a lot more draggier than a streamlined body, which is reflected by a high drag coefficient of 1.0 as opposed to 0.005. That makes sense.
Yes, it does. Thank you very much.
Yeah. Right, do you guys like have answers? It's like rho and v would cancel out, so you don't even have to worry about it. It's just like
Yeah,
ratios.
everyone already put stuff in the chat about that too.
But they did.
Yeah,
I didn't even
Uh,
like respond. Okay, good. So
yeah,
so imagine like if I draw it on scale and 0.15 centimeters, so that's 15 millimeters, right? 1.5 millimeters. Oh man, I need sleep. Yeah. It is like very tiny compared to an airfoil. So a shape that is cylindrical will have to be this small to match the drag of something this big that is streamlined. So if you were to like put this in wind and measure the forces acting on these things, this shape would experience the same drag as this shape, and you can consider and you can like see the difference in sizes. So a common concept that we as aerodynamicists do is when you have a draggy object like this, we put a fairing around it. So what we do, we enclose the shape within another shape like this. And what happens is this cylinder is now not facing the airflow. It's the airfoil that instead is facing this. So whatever functionality the cylinder was serving, it can still serve it. But because we now have covered it in a fairing like this, called a fairing, so when you put a streamlined object around a blunt object like this is a common way to reduce drag and make it go faster, or reduce the amount of forces acting on it. So with that in mind, now you know the difference between uh, um, a blunt object and a streamlined object and how much streamlining can have an effect on the aerodynamic performance of objects. Let's get into a little bit more qualitative discussion of different shapes and streamlining. Where's mine? I did a workshop for a different club, so I'm just gonna pick that up here, right here. So these are different shapes here. Don't worry about the 3D one now, just focus on this column here. We'll worry about this later on. So look at these values. Higher the value, the draggier the shape is for the same size and the same speed, okay? So obviously, if you have a flat plate facing the flow like this, it's going to have a lot of resistance as compared to an object that is lying flat and facing the wind. So that's just common sense, right? I mean, you would just like lay it flat to make it go faster. And you can see that in the CD value here, which is a lot lesser compared to something that is just standing upright like that. Another example is the triangle. So depending, it's the same triangle, but if you orient it in a different way, the drag coefficient changes dramatically, right? So the reason why is if you have an airflow going like this, the flow takes a path like that, and the region of dead air is much smaller as compared to, for example, like this, where the air flows like this and goes like that. So it ends up with a larger wake region behind it. So just by orienting the object in different ways can just have a lot of effect on drag reduction. Another thing that we need to worry about is sharp corners in any aerodynamic flow. So here's another one. this graph here. So if you have a square with sharp corner, the drag coefficient is 2. But as soon as you round it off even slightly, the drag coefficient can be significantly reduced, right? So this is the drop in the amount of CD you can get just by rounding off the corners slightly. And the more you do it, the more drag you end up reducing as a function of Reynolds number. So in aerodynamic design, we always want to avoid sharp corners, because at sharp corners, the flow just ends up separating from the surface and it creates all sorts of problems. But when you have corners like these, the flow, so um, instead of doing this, the air, because it's more rounded now, it tends to follow for a larger portion and remain attached and result in a lower dead air region part. So yeah, this so these concepts were like they're not like really relevant to us for a wind turbine blade design, but there are other aspects of a wind turbine where we need to make sure, for example, our rotor hub or like our tower or like other things, where we need to make sure that our objects are fairly well streamlined and it's not causing this massive wake region that disturbs the flow field around the other important components, right? So it's just something to consider. So now that you have had an introduction to bluff body and streamlined bodies, we can move on into discussion to high angle of attack aerodynamics. So from previous workshops, you might remember the geometry for an airfoil. So if you remember, the chord is, okay, so let's start with the leading edge. This is the leading edge. If this is facing the wind like this, then this is the leading edge. And this is the trailing edge. And this is the chord line, a straight line connecting the leading and trailing edge together. It's called a chord line. Okay, it's denoted by the letter C. The angle the chord line makes with the velocity vector is the angle of attack. It's not. So let me draw an airfoil at an angle. Okay. So this is the chord line. Let's say the velocity is horizontal and the angle that the airfoil is making with horizontal is 15 degrees. Then the angle of attack, denoted by alpha, is 15 degrees. Now, like I said, the angle is not between the chord line and the horizontal, but it's between the velocity and the chord line. So if the velocity was, let's say for the same example, if there's the airfoil and this is the chord line and the velocity, so the angle the airfoil is making with the horizontal is still 15 degrees, but the velocity vector is now slanted like this. The angle this thing is making is, let's say, 10 degrees with the horizontal. So can someone tell me what is the angle between the chord line and the velocity vector here? so the chord line is making 15 degrees with the horizontal, and V is making 10 degrees with the horizontal like this. So what is the angle between V and the chord? Can you guys hear me?
Yeah,
Yeah,
25.
we can hear you.
Yeah, okay. So the angle of attack in this case is then 25 degrees and not 15 degrees. This is a very important fact in wind turbine aerodynamics because wind is rarely horizontal, like the relative wind, and it's usually at an angle, and the airfoil is making a different angle with respect to horizontal, and it kind of like mess with your brain later on if you don't understand the angle of attack definition. It's the angle the chord makes with the velocity vector and not the horizontal. Okay, so alpha is 25 degrees. And what is the direction of lift and drag in this case? If the velocity vector is tilted 10 degrees to the horizontal, how would you draw lift and drag? Would you draw them vertical and horizontal like this? Is that the correct way to go about this?
You do it with the velocity vector parallel to drag and normal to lift.
Yeah, so another fact you need to remember is that drag is always defined parallel to V, and not its drag is not always horizontal. It depends on the direction in which the wind is flowing. Okay, the drag is always parallel to the velocity vector, and lift is always defined perpendicular to V. So in this case, if V is like this, then the drag force is parallel to V, and lift force is perpendicular to V. Like that. So I gave this example specifically because we're used to seeing velocity vector always horizontal. And because of that, lift always becomes vertical and drag always horizontal, but that's not always the case. So it's something to remember. And this will become useful when we do blade element momentum theory down the line, right? We also remember what is the relationship between the lift coefficient and angle of attack. So let's go with drag coefficient and angle of attack. Okay, so actually let me do the low angle of attack before stall first. Right. So here's an airfoil. V is parallel to the airfoil. Sorry, V is horizontal, and the angle of attack of the airfoil is gradually increased. Okay, so the angle of attack of the airfoil is gradually increased. What is the CD versus angle of attack going to look like? It's so because like I told you, the flat plate, when it's like standing as opposed to it lying down, this has lower drag compared to something like this, just because it has more projected area to the wind, and that results in higher resistance. So when you're increasing the angle of attack of the airfoil, you're increasing the amount of area the wind faces, and that ends up increasing the drag coefficient of the object. So the way it goes is it basically grows very steadily until you reach stall. I hope everyone remembers what stall is. So this is all recap. Okay, so this is not something new that I'm introducing here. This was all discussed before we move on to more advanced stuff. So here's an angle. And like I said, a streamlined body is the one where the flow follows the contour of the upper and lower surface completely without separating from the surface. But there's a limit up to how much you can increase this angle by before the flow decides to say enough is enough and I'm done, bye-bye. So if you increase the angle of attack more, it just separates like this and leaves a region of dead air called wake behind it. So in this case now, it has transitioned from being a streamlined body to a fully bluff body. And this condition where the flow is fully separated from the upper surface, it's called stall. Okay. Now, as you can imagine, if you go back to this example where the difference between a streamlined body and a bluff body in terms of drag coefficient, it's massive, right? It's orders of magnitude different. So when you have this stall, when you transition from being a streamlined body to a bluff body, you have this sudden increase in drag that shoots up like this. So this is beyond stall. You have a massive rise in CD as you increase the angle of attack more. The question is, what happens if you keep on increasing the angle of attack beyond stall? Because usually we don't bother about what happens after stall because it's not, the airfoil is basically useless for us once it has stalled because it's not a streamlined body anymore. But sometimes, especially in case of wind turbines, we do encounter situations where the airfoil has no choice but to operate under stall conditions. So it becomes useful for us to understand what happens beyond stall if you keep on increasing the angle of attack. So this stall angle is typically 10 to 15 degrees. So for most airfoils, if you increase 15 degrees angle of attack, you're most likely in the stall region. But what if I want to increase the angle of attack to, let's say, 45 degrees to just go crazy, or 90 degrees? What happens? So let's just imagine that. Let's just imagine the extreme case scenario where the angle of attack is 90 degrees. So let's say alpha is 90 degrees. So if the wind is flowing like this, you have an airfoil. This is alpha equals to 0. So if I have to increase the angle of attack to 90 degrees, it would look like this. Because the angle between the chord line and the velocity vector is 90 degrees this way, right? So it's basically like a flat plate perpendicular to the flow field. And it's basically a bluff body. Now, if you remember, what is the drag coefficient for a flat plate? Like this, it's almost 2, which is also true for something like this. The drag coefficient for this is, so you can imagine we were at a CD of, where is it, 0.005 when the angle of attack is low. But when you are at 90 degrees, the drag coefficient has increased to become 2.0, which is several orders of magnitude higher, right? why is the CD 2.0 for an airfoil perpendicular to the uh, to the flow field? If you look at this drag coefficient, sorry, equation for drag, which is half rho v square times the chord of the airfoil times the drag coefficient. If we put CD equals to 2 here, it becomes rho v square times c. We can write this as rho v v times v minus 0 times c, right? So it's basically what it's basically doing. It's telling you that if the flow field, if you had to imagine this flow field, then the region of air behind the flat plate, it's 0, right? You can assume 0 velocity right behind the flat plate and free stream velocity outside outside of the flat plate region. So this is basically the momentum equation you get when you do the control volume analysis, which is rho integral of rho times v minus v minus u, where u is the velocity here in the region, times c, going from 0 to infinity. So this is basically momentum balance, and it's as if the velocity behind the flat plate is 0. So when you do that, it results in a drag coefficient of 2. That's a good way to remember this. But this is for a flat plate. But because the airfoil has a rounded edge on the top, I told you the effect of rounding, right? It reduces drag, and it indeed does in this case as well, because in case of a flat plate, the flow field is just doing something like this, as opposed to an airfoil where the flow is able to remain attached longer, and it results in a lower dead air region thickness. And this results in a drag coefficient of 1.8 at 90 degrees as compared to 2 for a flat plate. So if we were to draw a diagram for drag versus angle of attack over 180 degrees, we know drag is very low at low angles of attack because the airfoil is streamlined, but then it increases dramatically to 2.0, nearly 2.0, well, 1.8-ish. So let's say somewhere here, right? So it's going to do something like this, where the drag is the highest at 90 degrees. Why is this is actually a very bad drawing. It's going to look something like this. What happens beyond 90 degrees? So 90 degrees is when the airfoil is like that. Let's say it becomes 110 degrees. In that case, the airfoil is now like this to the wind, and the amount of projected area to the wind is lower than the 90-degree case. So the drag coefficient goes down again until the airfoil becomes 180 degrees, where it is, I don't know how to draw a reverse airfoil. Hang on, just try my best. Like that. It's crappy airfoil, but take my word for it. It goes back to 0. like that. So we know two values. It's very close to zero. The drag coefficient, sorry, this is CD, not D. So CD is very close to zero when the angles of attack are very small in this region, which is what we want. But when you increase the angle of attack beyond stall, let's say this is alpha stall, the drag coefficient rises dramatically. But what happens to, what about values intermediate? We know 90 degrees it's 2 and close to 0 at 0 and 180 degrees. But at 45-degree example, for example, what is the drag coefficient? It's usually 1.1. And I'll explain why. So we know for 90-degree case, CD is approximately 1.8 to 2.0, right? If you do 45-degree, you can imagine it to be an equivalent airfoil like this, whose chord length is, let's say this is C, then this is C sine 45. You can imagine this to be an airfoil that is that has a chord length of C sine 45. So the drag coefficients will scale by sine 45, right? So if you do 1.8 times sine 45, can someone tell me what this value is? It should be very close to 1.1.
It's 1.27.
Right. So this CD for an airfoil at a 45-degree angle of attack would be close to 1.27, you said?
Yeah.
Right. But in practice, it's a little bit lower than 1.27 because of this rounded edge effect. Because the airfoil is at a lower angle and it has a rounded leading edge, the flow remains attached on it for a longer portion. So instead of separating here, it might like separate somewhere here and result in a lower wake region. So the CD in practice turns out to be close to 1.1. Can you say something about the CL at 45-degree angle of attack based on what the CD value is? What is the relationship between drag and lift if the angle of attack is 45 degrees? They're both going to be equal, right? Does everyone get that? I can prove it. I'll just prove it.
Yeah, can you show that?
Yeah. So let's say because the wind is horizontal, the lift would be vertical, i.e. perpendicular to the velocity, and drag parallel to the velocity. So if this angle is 45 degrees, and if primarily the force on the airfoil would be perpendicular to the chord, because most of it is it's just separated flow.
Suraj, I think you might be drawing off screen right now.
Oops, sorry about that. Thank you. So most of the force is perpendicular to the chord because it's just a bluff body. Remember, it's a bluff body. So the net force is just going to be perpendicular to the chord, and because this angle is 45 degrees, if this is 90 and this is 45, then this has to be 45 degrees. And if this is 45 degrees, then L equals to D. So if drag is 1.1 CD, then CL is also going to be 1.1 at alpha equals to 45 degree. Yeah, I'm gonna have to zoom out a little bit. All right, so we know what the shape of the drag curve looks like over 180-degree angle of attack. What about lift? Let's go back here and draw a separate diagram. Can somebody tell me what a CL versus alpha curve look like before it stalls?
Linear.
So let's say I draw and this is the stall angle. What would the CL versus alpha curve look like in this region between 0 and alpha stall? You guys don't have to be shy. Like, it's not an exam. If you're wrong, it's fine. I just like want you guys to participate. Otherwise, it feels like a lecture, which I don't want this to be. So so this is it's a straight line. Remember, with the slope of 2 pi alpha, 2 pi. If you increase the angle of attack, then CL increases with angle of attack in a linear fashion up to stall angle, after which it drops like this, CL value. And the reason why it drops was explained in the previous workshop, but has to do with flow separation and that the flow is not able to flow over the curved surface and it's not producing enough pressure difference across the airfoil that results in a drop in lift coefficient. But we left it at that. We don't know what happens if you keep on increasing the angle of attack much beyond stall angle. And that's what we'll discuss today. So let's go back to the 90-degree case again, right here. So if wind is flowing in this direction, what is the direction of the lift force? Is it going to be perpendicular to the airfoil or perpendicular to the wind? Lift is, sorry, say that again.
Perpendicular to the wind.
Right, so the lift force will be acting like this, and this is the drag force, right? So CD of 1.8, but because the force is primarily in this direction, there's zero or little lift force generated when the airfoil is at 90-degree angle of attack to the wind. Okay, so we already know at 90 degrees, the CL would have to go to 0. And we know CL at 45 degrees is 1.1. So we can now draw the lift curve slope, lift curve as a function of angle of attack. Let's call this alpha stall, 45 degrees, 90 degrees, 135, 180. Okay, so this goes up to a typical CL max at alpha stall. You can assume it to be 1.2 or 1.1. And this is for like a symmetrical airfoil. If you have a cambered airfoil, you can get way more CL max out of it. But let's just keep it simple for now. So we know between 0 and alpha stall, the lift goes linearly. So let's draw a linear curve. And what universe is that? A straight line? Let me again. I give up. Let's just assume it's a straight line. And then it drops down like that. But then at 45-degree, we know that the lift coefficient would be 1.1. So it has to increase back like that. And then at 90 degrees, we know it has to come to 0. Now the question is what happens when you increase the angle of attack beyond 90 degrees. So when the airfoil is slanted like this, in what direction will the lift force be acting? Lift will still be acting perpendicular to wind, but if you
Negative.
yes, exactly. So now actually it's acting below the airfoil instead of above the airfoil, right? So the direction reverses. Does everyone get that? Why it's going to be negative? So you have an airfoil. So lift typically acts above the in the direction of the upper surface. So this is the upper surface, and this is the lower surface, right? So the lift that is acting is now acting downward, like toward the lower surface more than the upper surface. So it's going to reverse its direction. And at 135 degrees, it's going to have the same lift coefficient of 1.1 because it's just 45 degrees from the other side, right? Everyone gets that? So it's going to be minus 1.1 and then go all the way down like this. And then back to 180 degrees, where, wait, 90, 135, 180. 180 is, crap, I forgot like what's gonna be like. At 180 degrees, it's parallel, so I feel like it should be generating non-zero lift, right? So it shouldn't be 0. So
No, it would be, if it was symmetrical, it would be 0. Yeah.
oh yeah, you're right. If it's
It might
symmetrical,
have another stall and whatever too, but except the flow might reattach, but it would be so
yeah, you're right.
negligible because the airfoil is now like the air is hitting the point first.
Mhm.
Yeah.
So if the airfoil is actually like this is the leading edge. And if this is a symmetrical airfoil, then the pressure difference on the upper and lower surfaces are equal. So at 0 degree, this is basically like 0 degree, but inverted airfoil. So it goes back to 0 like that. Right? So this is what the curves look like. Now, unfortunately, most tools that we have at our disposal, like Xfoil and stuff, they only analyze stuff in this below stall region. So we have to use tools like WTPerf from NREL. That will, based on the airfoil data in the linear region or the pre-stall region, it will provide you with an airfoil data for the 180-degree angle of attack based on their empirical modeling and relations. So it's just like an Excel sheet from what I remember that you just have to like give some input, and then it will generate 180-degree angle of attack airfoil data for you that you can then use for wind turbine analysis. So it's already more than 1 hour right now. I don't want to like keep you way longer, but I will just leave you with an overview of what blade element momentum theory looks like, and then next time we can begin with that. But before I do that, do you have any questions on whatever was covered today? I know I threw a lot of technical stuff at you, so it might be a little bit overwhelming.
What's the WTPEF that you wrote down there again? What was that?
It's WT perf, which
Yeah.
means wind turbine performance. It's a code that you can download for free to analyze the airflow data for 180-degree angle.
Is it similar to X1 or is it like just give it the shape and
Yeah, so you have to provide a code with the data in this region before the stall region, and then it extrapolates the airflow performance over 180 degrees based on what you give it.
or just have to give it that first region and
Yeah,
figure out the rest?
it's just extrapolating, but it's extrapolating in a smart way, knowing the general behavior of airfoils. There's a
Wow.
couple of models, mathematical models. Like I think one of them is called Montgomery, and one of them is called Viterna, I think. And there might be others as well.
Viterna is a post-stall model. It's a different thing.
Okay,
Yeah.
Montgomery, I think though, is a extrapolation tool.
Yeah.
Or it's not like Montgomery is the name of the guy that came up with the formula, and then the tool is called WT-PERF.
Yeah.
And the reason why we need to know like the entire 180-degree performance will come in later in the blade elements, right? I assume.
It's like
Yeah,
during wind turbine analysis, when you were trying to get like the CP curve, and CP is power coefficient. We'll cover all of that in the future workshops. But when you're trying to extract data for wind turbines in the off design conditions, you design the wind turbine to operate in a certain condition, but because winds are rarely constant, they're always changing. To calculate AEP, we need to know the performance across a wide range of tip speed ratios, for example. So you gotta like,
it's very unlikely that you'd be using the data for like 180, but it's there just in case the code needs to, in case something weird happens, basically.
exactly. You can go as high as like 30 degrees, for example, which is still very high.
Yeah.
So it's just like, you never know how far, like it depends on your operating conditions on how far you want to go. So if you give the code only 30 degrees and it wants the data for 35 degrees, for example, the code will like not analyze that portion of your performance. So it's just better to give it everything, and then it can just like determine what it needs for that.
Oh, that makes sense.
Any questions about any of the stuff here?
I don't have a question. I just have a suggestion. So is it okay if you use thicker lines next time? So because some colors pretty hard to see.
Sorry, say that again.
Is it possible to use thicker lines to write? Because the red color is pretty hard to see at some part.
Oh, red color. Oh, thank you for bringing it. I'll try to use like I'll maybe stick to white and brighter colors.
Yeah, thank you.
Yeah. And like if you have any issues like this during the workshop, just tell me immediately, and like I would just switch, next time.
Okay. I could still see it, but just pretty hard, and my eyes were tired.
After 1 hour, yeah.
All right. I guess I could switch to white background too, if that helps. I feel like, I don't know why it's black for me. Let me see if white background helps.
Well, yeah, it won't for this particular one, but the white lines will go away. But this oh, they don't. Look at that. This is clever.
No, yeah, it just like turns black.
Huh.
I feel like I could like change the color or like the settings of thickness of the pen, but
The
do you think
thickness.
white background looks better than black?
I prefer black, just my personal opinion, but both
Yeah,
work.
this is very bright actually.
Mhm.
Maybe we just my
Is it a
screen
good
is too
thing
bright.
or a bad thing? Very bright.
Yeah,
It's a bit too bright.
Guess it's not a good thing.
it's
right?
okay. I can deal with it. I mean, it's
All right,
still
so
usable.
I'll stick to black and change strategy on the pen settings.
But make it bright might make it more get more attention.
All
There
right.
you go.
Yeah, I'm a fan of dark stuff too. Everything dark on my desktop. But yeah, okay. Well, why don't I just play around with it now? Why don't you tell me what color works for you? I don't have a lot of choices here. It's blue, red, yellow.
It's more the width, I think. Any color is okay. Although the blue and the green are a bit dark. On the dark, the red is.
Okay, I'm gonna just scribble here and then you can tell me which colors are best. White works, right? White
Yeah,
is
white
good.
is good.
Okay, white is good. What about
While we're
green?
talking about pen stuff, do we want to turn off the recording?
Oh yeah, I was gonna say that too. Yeah.
Oh yeah. Good point. Stop share. How do I stop this?
Oh, you might not be able to stop it till the thing is done. You can crop it on the YouTube though. Probably.
Just stop sharing. No, wait, I still need to do
Sure,
my,
yeah.
yeah.
Change it to the different style of pen at the top. There's like a bunch of choices up there. Like, is there a wider one? Which one are you using right now?
So I'm using my tablet, right? So it has limited choices.
No, at the top, there's some things.
Yeah,
can see?
that's
Okay.
only accessible on my desktop, not on my tablet.
Oh,
So I'm like
Oh.
annotating on my tablet and it like syncs up on my desktop. So is green okay?
It's a bit harder to see. I think. Oh, okay, it's bigger now. Yeah, actually, that's not too bad.
Okay, so green is a go. What about this shade of blue? Is this hard to read?
that's good.
Patty?
Yeah, it looks fine.
It's fine. Okay, so I gotta like remember two things: no red color and no creepy smiley emoji for her. What about pink?
That's fun.
Yeah.
Okay, so the only color you have issues with is the red. I'll remember that. All right, great. Okay, so if you don't have questions now, but you have it later, you can DM me or like Andrew or like anyone basically.
Yeah,
Yeah,
you
like
can
don't
reach me on
hesitate to
Slack.
ask questions. Sorry, say that again.
I'm just saying, yeah, you could reach us on Slack.
Exactly. All right, so I'll stop sharing. I gotta like do my experiments too. So.
All right, see you guys. Good. Thanks, Suraj. That's good.
Thank you
Yeah,
so much.
thanks, Suraj.
See you.